Good day, our dear listeners. Today we will have another lesson on the computer science from the program of grade 11. Presentation is prepared by Кажгалиева Еркинова, teacher of computer science of NIS program. Today's topic is algorithms. Let's look at this, remember what is that, and look at some algorithmic machines. The key words and phrases that will be used here on the lesson are algorithm, flowchart, input-output, pseudocode, decision, process, flowline, state, input string, head, and tape. If you have any idea what these words mean, it will be great if you just say me the definition or your understanding. If you haven't ever heard about that, that's also okay, because we'll just look at this on this lesson. First, look at these questions. What is an algorithm? You have 1 minute to find an answer. And an answer is given below. Algorithm is a set of steps or instructions that complete a task. This is a basic way of demonstrating how a computer program works. A simple way of visually demonstrating an algorithm is by using a flowchart. We know what is an algorithm from grade 8, grade 7, I think. Now we'll just remind some basic concepts and look at Turing machine as an example of algorithmic machine. How we can represent an algorithm using some symbols. Here are given the basic ones, like a start or end of the program, an input, shape, a decision to be made, a process to be carried out. Flow line shows how the program flows. Using these 5 shapes, you can draw any algorithm, any simple algorithm. Like this. Make a flowchart to demonstrate the decisions made for making a cup of tea, but this time ask if sugar, milk, or lemon are required. Firstly, you can see that the easiest algorithm is given when you just make a tea using a boiled water, but you have to try by yourself to make a cup of tea with different choices, like do you need sugar, milk, or lemon, or anything else. And you have to remember that you can make the chart as simple or as complicated as you like by adding more decisions. Also, note that when a decision takes place, the flow may have to loop until the correct answer is available. If you look at this diagram, you can see that if the water is not boiled, you have to switch on power all the time. It makes a loop. Now your task to construct a making sandwich flowchart. It should contain at least 2 decisions. You have 15 minutes, it can be as complicated as you wish. If you finish early, format for easier viewing and save in your backpack in Edmodo. And also you have to know that when you make a decision in your flowchart, it can create a loop also. And you have to think about, do you need any loops in creating sandwiches? Because it will become a big sandwich if you just try to put all the time meat or bagel or something else. Let's look at another way to represent the algorithm, a pseudocode. A pseudocode is a way of writing syntax in a way that is understandable with no experience of coding. Let's look at this flowchart and pseudocode. In the pseudocode, there are three main parts: input, process, and output. Here you can see that pseudocode begins and the program is called flat tire. There is a decision: if tire is flat, then stop car, else keep driving. And another decision: if you are in car, then exit car. And there is an end of this decision. And the process means that you have to open boot, get jack and spare tire, put jack on the car, repeat pumping jack, doing everything just to change your flat tire. The same thing you can see in the flowchart. These two parts, in the left and in the right, are representing the same thing. Now we remembered what does algorithms mean, and now let's look at the example of algorithmic machine. As an example, let's look at Turing machine. How do you think, what is the Turing machine used for? And how do you think, what parts can be in this machine? Let's look at the first question. There is another question. Is a Turing machine a computer? The answer is no. Turing machines are not intended to model computers, but rather they are intended to model computation itself. There are a number of ways to explain why Turing machines are useful models of real computers. You can see that going by link here given to a Wikipedia about Turing machine. Turing machine is a thinking machine, a model that can compute anything that a human can compute. Before the invention of electronic computers, the term computer actually referred to a person whose line of work is to calculate numeric quantities. As this is a philosophical endeavor, it can't really be proved. Turing's thesis is any algorithm can be carried out by one of his machines. Imagine a super organized, obsessive-compulsive human computer. The computer wants to avoid mistakes, so everything written down is completely specified one letter or number at a time. The computer follows a finite set of rules which are referred to every time another symbol is written down. Rules are such that at any given time only one rule is active, so no ambiguity can arise. Each rule activates another rule depending on what letter or number is currently read. Let's look at the parts of the Turing machine. The main part of the Turing machine is called tape. And also it is the main reason why Turing machine is not the real one. It is an abstract because the tape, the idea of Turing machine that the tape has to be an infinite one. And it's not a realistic thing, and therefore we say that Turing machine is an abstract machine. Except tape, we have a read-write head and a control unit. The tape, as we said before, have no boundaries. It is an infinite length. And the head can move left or right. This head can do any of the transitions or operations below. It can read a symbol, it can write a symbol, it can move left or right. For example, let's look at the tape that is given first and the operations that are given below. The head have to read. If it reads the letter A, it has to write K instead of A and move to left. And we see the result in time 1, we see that the letter A was changed to the letter K, and the tape and arrow moved left. Another operation. If the head reads B, it has to write F instead of B and move right. And also here you can see the result of that. Another part of the Turing machine or Turing algorithm is the input string. Input string is the string of the numbers or symbols that you give initially. And except these symbols and numbers, there will be another cells that are have no symbols or no numbers. They are called blank symbols. They can be represented in any letter or symbol. Here you can see they are in form of rhombus. Head starts usually at the leftmost position of the input string. How can we write the actions? There are different ways, in form of table, as an operation codes, and in form of flow diagram. Let's look at the diagram. States and transitions in the diagram are represented as here. The letters Q1 and Q2 represent the states. The starting state here is Q1, and in this state the head reads letter A. It has to write the letter B instead of A, move the head left, and change the state to Q2. Instead of left, we can write right, to move right. Let's look at this example. Head is on the position with the letter A. And the current state is Q1. Below, you can see the diagram that shows then an action. What we have to do. If the state is Q1 and it reads letter A, it has to change the letter A to letter B, move right, and change the state to Q2. Here is the result. You can see that our head moved to right and changed the letter. What if we change the letter R instead of letter L? It will go to left and change the state also. Another action with blank cells. If head reads blank cell in state Q1, it has to write the letter G, move to right, and change the state to Q2. If we don't change the state to Q2, it will be an infinite loop, because all the time it will see the blank in the right and it will not change the state. There are several rules in Turing machine. The first one is Turing machines are deterministic. No lambda transitions are allowed. For example, look at the first diagram. In the state Q1, if the machine sees A, it has to change it to letter B, go right, and change the state to Q2. In the state Q1, if the head sees B, it has to change to D, move left, and change the state to Q3. This action will work on the Turing machine. But another diagram on the right will not work on the Turing machine. Why do you think it is so? Look at the diagram carefully. You can see here that there are two actions given for the same condition. If in the state Q1 it will see A, first action says that it has to change to B and go to right, and another operation says that it has to change to D and go left. Machine doesn't know what to do, and therefore this algorithm doesn't work. There is another concept like a partial transition function. What does it mean? Here in the diagram we can see that in the state Q1, machine has to change the letter A to letter B if there is that, and if there is a letter B, it has to change it to letter D. But there is no transition for input symbol C. Therefore, here it will stop. It doesn't know where to go next. Halting. The machine halts in a state if there is no transition to follow. There are two situations to halt. First example, no transition from Q1. We have no flows going out Q1, therefore it stops, halt. Or another example, no possible transitions from Q1 and symbol C, as we said before. In this situation, it also stops. What is accepting state? Accepting state is the state when our machine has to stop and give a result. Accepting states have no outgoing transitions, and the machine halts and accepts. What was the result? Acceptance means accept input string if machine halts in an accept state, but reject input string if machine halts in non-accept state or machine enters an infinite loop. These strings will not be accepted. Observation. In order to accept an input string, it is not necessary to scan all the symbols in the string. Let's look at several examples. This algorithm accepts the language of A's. It means you can use any number of letter A in the input string. Here is given an input string with 3 A's and an action table below. In state Q0, if you see A, it has to change it to. You don't have to change that. Move right and leave the state in Q0. Next step, doing the same. Third time. When see it blank, it has to leave blank, go left, and change the state to Q1, accept, and halt. An example of rejection. The same action, but another input string. Here also with letters A, we see the letter B. But in our action diagram, we can't see any transition to letter B. It means when it sees A, it leaves it as it is, go right, and leave the state also. But for the letter B, there is no possible transition, and therefore it halt and reject. A simple machine for assembly language, but for input alphabet A's. Accept the language A, and the action is given below. It is only acceptance state Q0. It means that it accepts only this state and stops, halts here. Therefore, no necessary to scan input. Here is an example of infinite loop. You can see a diagram below and input string is given on the top. Let's look through this algorithm. When it sees a letter A in state Q0, it have to leave the letter, move right, and leave the state. The same, when it sees letter B, it will leave this letter, go left, leave the state. What else? What is next? The same as the first step. Time 2, it will go from A to B. Time 3, it will go from B to A, and again from A to B, and etc. and etc. And that is why it is an infinite loop. Because of the infinite loop, the accepting state cannot be reached. The machine never halts, and the input string is rejected. Another Turing machine example. Let's look at this example. The basic idea of this example is match A's and B's and repeat. Replace leftmost A with X, find leftmost B and replace it with Y until there are no more A's or B's. If there is a remaining A or B, reject. First time. Just look at the diagram below. If it finds A instead Q0, it will change it to X, go right, and change the state to Q1. Next step, leaves A, go right, changes B to Y, go left, just to look, are there any B's or Y's? Let's look again. From the beginning, the next leftmost A, changed to X, leftmost B, changed to Y, checking everything again. Now we came to blank, and therefore it is an accept state and it halts. Formal definitions for Turing machines. Transition functions can be written not only in a diagram form, but also in a formal transition, like it is given below. You can see that the first function, sigma q1, c, gives the initial state and initial symbol. After the sign of equal, there is a q2, d, and l, means that the state will change to q2, the symbol changes to d, and it goes to left. In general, the function of Turing machine uses these types of things, like states, like q1, q2, and etc. Input alphabet, it may be 0, 1, or A, B, C, or everything like that. Tape alphabet, it is an initial tape. Transition function, we say that action function. Initial state, the state from which it begins. Blank, cells that are not filled. And accept states, the state where it has to stop. Computing functions with Turing machine. We know what is decimal number and what is binary number. And also, we know what is unary number. Unary numbers, have you ever tried to count when you was a child? Like one finger means 1, 2 fingers means 2, and etc. The number of zeros represents the number itself. We prefer unary representation because it is easier to manipulate with Turing machine. Let's look at this example. We have to compute the function x plus y, where x and y are unary integers. Input string has to look like x, 0, y, and output string will look like x, y, 0. As all the numbers of x and y consist only zeros, only ones, the 0 will represent the delimiter that separates the two numbers. In the start, we have to see a number of ones that represents x and the 0, and the number of ones represent y. At the end, we have to see the number of ones that represent x plus y. It will be the sum of them. And at the end, we will see 0. It will be go to the end. The 0 here helps when we use the result for other operations. And in order to make it easier for you, here is the given action diagram for all operations. Let's try it with the initial tape, like 1, 1 for x and 1, 1 for y, and 0 as a delimiter. As the final, we have to see the tape that is given below. Let's start from the beginning. When the machine sees 1 in state Q1, it has to leave it as it is and go right. The same thing. When it sees 0, it has to change it to 1, go right. In the state Q1, when it sees 1, it leaves 1 and go right. We came to blank. When head reads blank, it will leave blank, go left, and change the state to Q2. In the state Q2, it changes 1 to 0, goes left, and the state will be Q3. In the state Q3, we'll look through all the ones going left, and if it comes to blank, it leaves blank, goes right, accept, and halt. Here are 3 examples, 3 tasks for you just to try at home. The easiest one of them, in binary system, add 1 to any number. Also, in binary system, if the number is positive, starts from plus, add 0 at the beginning, and if the number is negative, starts from minus, write this number in 1's complement. If you remember what does mean 1's complement and 2's complement, because the next task is in binary system, if the number is positive, starts from plus, add 0 at the beginning, and if the number is negative, starts from minus, write this number in 2's complement. I hope that everything was interesting for you and understandable. If you have any questions, I will be very happy to answer them. Thank you for your attention.